Yes, so we are again, how was your experience with EFA? Anybody? Okay. Okay, thank you. So we are starting, I'm sharing my screen. We are starting with confirmatory factor analysis. So you now, I think all of you should note your factor structure also, because what factor structure you have proposed in exploratory factor analysis, now we'll enter that factor structure in confirmatory factor analysis. And few important points which we discussed earlier also, but I would like to repeat it, that you will not do the confirmatory factor analysis on the same sample on which you have done the exploratory factor analysis. So exploratory factor analysis is basically to explore the underlying factor structure, and confirmatory factor analysis is to test that particular factor structure. So how to do this, we'll see. So you can see that we have learned that if you start with 6 factors and there are 6 items, so initially you assume that each item will measure one factor. So there are 6 initial factors. So each item, it has to be assumed that the total variance is 1 unit. So now let's see this process again. That if you see, the first item that is getting loaded on all the 6 factors. Maybe proportion, you can see that it's variable. It has got larger proportion here on factor 1, whereas if you see factor 2, item 2 is loading here to the larger extent. So similar, the concept is each of these items is getting loaded on all those 6 factors. The proportion might differ. That means the amount of factor loading will be different for all items in all the factors. But like you have seen that matrix, if you factor loading, if you like reduce it to 0, you can see that each item is getting loaded on all the factors. Are you clear? That's the basic concept of a classical measurement theory, that each item will be loaded on each factor, but we take only the strong loading. And what do we mean by strong loading? That it should be at least 0.5 or more than 0.5. That is the meaning of strong loading. And again, we learned that if on one factor at least 2 items should be of strong loading, then only you will consider that as a factor. Because then only the eigenvalue will be more than 1. Because if the value is less than 0.5, then the eigenvalue will not be more than 1. So in this case, the 100% variance in any of the item, it never get explained by all the factors of a construct. So there will be some unexplained variance, which we call it as a measurement error. So now coming to the validity. Now we will, in confirmatory factor analysis, we talk about validity. Till now, we have only talked about validity before reliability. When we were finalizing the items in the scale, then at that time we talked about the content validity, where the 2 types of content validity, the subjective as well as objective. Subjective content validity was just to see the face validity and the clarity and all those less of ambiguity, it was there. And the objective criteria, more objective, where you take the expert review, you calculate the content validity index or content validity ratio, depending on the any method which we have shown with one of the method, but you can use like universal agreement or any other method also. But generally, most commonly, that is the overall scale content validity index and the item-wise content validity, where we have kept a cutoff of 0.8. It should be more than 0.8, each item and overall scale also. So coming to the other types of validity. So what do we mean by validity? we have learned that a good reliability doesn't mean that the scale will be valid, because items are correlated with each other. But we have also learned that the reliability coefficient has some limitation, because even if there are high number of items, large number of items, reliability increases with increasing the number of items. And even if only 0.14 inter-item correlation is there, and if it is a 25 question item, then your reliability will be more than 0.8. So to see whether the item which it is measuring, whether it is measuring the same construct which we have defined or not, for that you need to study the other type of validity, and that's we call it as a validity study or the validation exercise. So what is a scale validity? So basically a scale validity concerns whether the items which we have used, they are all correlated, but are they measuring the construct which we have defined? So yes, they are measuring the same construct. That will be very much clear from the inter-item correlation. But are they measuring the same construct which we have defined? So that is we mean by the reliability. So the adequacy of a scale, like how specific it is measuring that particular latent variable, that is the issue of validity. So we have done this flow chart previous also. So there's a content validity, there is a construct validity, and there is a current validity. So we have discussed this. We have discussed this content validity. Now we'll see this construct validity and the concurrent validity. So if you see the construct and concurrent validity, it is of two types. The construct validity can be classified into a convergent validity and a discriminant validity. So we'll see one by one what are the measures in confirmatory factor analysis to check for the convergent and discriminant validity. So coming to convergent validity first. So what do you mean by convergent validity? Yes, anyone? What do you mean by convergent validity? So as you have seen in case of a factor structure, the factor 1, it was comprised of, if you use that oblique rotation, I think factor 4, if I have written that, factor 4, 7, 10, 11, 12, and 14, it was getting loaded on one factor. And in factor 2, it was 3, 5, 6, and 13 item. And in factor 3, it was 8 and 9 number item. So there were 3 factor structure and there were underlying items. So the underlying items, how it has merged your exploratory factor analysis has merged all these items together into one factor. So is there any correlation between these particular item to measure the same factor? That we call it as a convergent validity. And how we measure this? So this convergent validity, basically it says that item within each factor. So this you can see, this is factor 1. If I show you with, so this is factor 1, this is factor 2, and this is factor 3. And if you see, like, these are the items measuring the factor 1. These are the items for factor 2. Sorry, this is for the factor 1. The upper one was for factor 3. So convergent, what this convergent validity says, that says that within these each factor, the items are sufficiently related to this factor and they are related with one another. So that they are all measuring the underlying construct. That we mean by the construct validity, and the specific of construct is the convergent validity. So you can see that this as a 1, the second was this, and so all these 3 factors, all the items within each factor are sufficiently related. Let me erase this, otherwise. So like if the this TQ, that is the Toronto Empathy Questionnaire, let's say like it has got a theoretical three factors: emotional empathy, cognitive empathy, and compassionate empathy. So a very strong convergent validity would mean that items within each of these factors are sufficiently related to each other, and together they capture that particular construct or factor. That means all the items measuring emotional empathy is measuring the emotional empathy. All items measuring cognitive empathy is measuring the cognitive empathy, and similar the compassionate empathy. So there are ways to check that statistically. So how to measure this sufficiently related, or in other words, how to measure the convergent validity, because sufficiently related means the convergent validity. So basically there are three approaches to measure, to report the convergent validity. So the first two is very objective, and third one is again objective, but less objective than the first and second. So coming to the first one is also known as the AVE, or the average variance extracted. It is a very commonly done reported measure to report for the convergent validity. And the catch point is here is the average. So what is this average? If you can recall that factor structure, there are various loading of that particular item on that factor. So amount of variance, how do we calculate variance? If you square that particular loading, it will be the variance. So amount of variance captured by items in that factor is, and if you take an average, it is known as the average variance extracted. There are three terms: average, then you have to take the mean. Variance means that loading square will be the variance, and extracted means that factor is extracting that much variance. So let's say if I talk about the factor 1. So these are the 4 items. This is just for example of factor 1. So like the first item is, it upsets me to see someone being treated disrespectfully. The second is, I enjoy making other people feel better. The third is, I have tender concern, feeling for people less fortunate than me. And fourth is, I get a strong urge to help when I see someone who is upset. So if you see this, so these are the various factor loading. So 0.64 is for the first item, 0.47 is for the second, 0.55 is for the third, and 0.64 is for the fourth. So what I will do, how to take out the variance? So you just square this. So the next will be, you just square this. So your amount of variance explained would be 40% in case of factor 1. I mean item 1, 22% for the item 2, 30% for the item 3, and 41% for the item 4. And you take an average of this. So if you just add it and divide it by 4, if you add all these 4 measure, 41, yes, all of you please do this. 41 plus 22 plus 30 plus 41. Again, those of you who are very good in maths, you can do it like 40, 40, 82 plus 82. It will be 104 and 134. So 134 divided by 4. It will be something 0.33. Yes, you can do it. Is it the same value which you are seeing here, 34%, or some other value? Are you people there?
It's coming around 33 point something, ma'am. Like, so.
Yes. So you can see this 0.33335. So
Yes.
approximately 34%. But the threshold is, it should be at least 50%, means 0.5 or high. That means if the variance is more than 50%, then only you can say that there is a convergent validity. So with this indicator, you can say that they are not convergent. So the convergent validity is not there in this construct. Because since we have used the same data and the average variance extracted, that total variance explained was only very less. How much was the total variance explained in that factor analysis? Yes. Can someone tell me the value? Yes, it was very less, 29.8 or 6, so it is approximately 30%.
30%, yeah.
And at least it should be 60%. That's the cutoff. At least 60% variation in the item should be explained by the latent factor. But don't get disheartened by this figure, because we are repeatedly saying that this is the data which we have received, and we have not told anything to the participant. You have just sent them the Google form. So there's a diverse data. So we can't say about the credibility of the data in that case. So that's why. But again, using the same measure, you can say that the convergent validity is not met in this case, although there is a factor structure. So have you understood what is the average variance explained? All that loading, we will do it here. We'll see in, and this you don't have to do it manually. You get this output in the JASP. And that's why we have chosen, like, very few participants in the beginning, they were inquiring why we have chosen JASP over Jamovi. So Jamovi and JASP is very much similar till you do the exploratory factor analysis. But for confirmatory factor analysis, you will see that JASP has got better feature than Jamovi, because Jamovi doesn't give you these values of average variance explained, or we will talk about the other, like composite reliability. Even the path diagram which you see here, it doesn't give you the loading, individual standardized loading, Jamovi. I will show you over Jamovi also. What is the difference between Jamovi and JASP? So the best till now was if you see all the internet and all the articles, most of them have used AMOS, SPSS AMOS for this confirmatory factor analysis and for the structured equation modeling. But AMOS, again, I said that it's a costly software and everyone cannot purchase it. Even if you purchase it, there is an issue with it is not very user friendly. There are many plugins, and we have, like, Dr. Shamshad was also tried and I was also there. So we tried, but we did not find it very user friendly. So that's why even we now onto this JASP for confirmatory factor analysis. So you know what is this average variance explained. Now coming to, and then again you may give the name of this factor. The second is approach is to known as the composite reliability. Now what is this composite reliability? So the catch point here is the composite. What do you mean by composite? We have done the reliability earlier also, the McDonald omega and the Cronbach alpha. But this reliability is different from the previous reliability, because here what it does, it takes the factor loading and the measurement errors of all the item. So what is the cutoff? So a cutoff value of 0.7 or higher is generally indicative of good convergent value. So you can remember the value of Cronbach alpha. There also we have read that the value should be more than 0.7. So the same value you can remember, the composite reliability, but it takes into account that measurement error also, where you will find that in case of reliability, that doesn't calculate for the measurement error. This composite reliability takes into account of that measurement error also. So this how it is different from composite reliability. Here in in Cronbach alpha, it assumes that all the items are of equal weight, whereas in composite reliability, you don't assume. You see that item which gets loaded with a strong loading, you take the weighted contribution of that particular item. So you can calculate, I mean, we will just show how to do this calculation of composite reliability. So suppose in this case, you can see we are showing it only with 3 factors, and you can see the composite reliability of each factor that you see as an output. So suppose we are only telling you with this 3 item, and you can see the respective factor loading. So if you see the respective factor loading, 0.7 is for the first factor, 0.8 is for the factor loading of item, 1 factor, and this is for the third item. So it is for 1 factor, and you take all the items, means it is lambda. Basically, if you see, it is the lambda, because you take the loading. So lambda, we have done it. So this is the lambda. which we have shown you. So now you square each of these items. And this is only for one factor, because empathy, like we have seen, it is with three factors. So we are only taking one factor because the composite reliability is factor wise. So you do the square of each of these items. So then what you do, square of this 0.7. Let me erase this. Square of 0.7 will be 0.49. This will be the square of each factor loading. Each matlab means factor item loading. I should not say, I use the term factor loading, but it is the loading of an item on particular factor. So you square these factor loading, like 0.49 for the first item, 0.64 for the second, and 0.36 for the third. Then how will you calculate the error variance? So 1 minus this is the error variance. So your error variance will be 0.51 for item 1, 0.36 for item 2, and 0.64 for item 3. So then what you do, basically, the formula is you add all the squared factor loading. So you add this 0.49 plus 0.64 plus 0.36. It will give you a square factor loading of 1.49. And you add these error variances also. So all these error variances like 0.51 plus 0.36 plus 0.64, it will be 1.51. So what is the formula? So if you see the formula of composite reliability, in the numerator, you take the sum of squared factor loading. And in denominator, you take the sum of squared factor loading plus sum of error variances. So what I will do, 1.49, because this is the sum of squared factor loading. And in the denominator, I will take the 1.49 plus 1.51. So it will be like 0.497. So if you see the value, what we said, that average value should be more than 0.7, because remember reliability, the value is same as composite, Cronbach alpha, but it is less than 0.7. So we can say that the convergent validity has not met. There is no convergent validity. So till now we have done two objectively measure convergent validity. First was average variance explained. What we did in the average variance explained, we took all the items of a factor, we squared those items and added and take a average of that. Average variance extracted. Average means mean of all the variances, individual variance of the factor, each of the item in a factor. In composite reliability, we take account of the error variances also. So in the numerator, what we did, we just added we added all those factors and we take the squared of factor loading. And in denominator, in that squared factor loading, we added the error variances. And this gives you the value of composite reliability. The value of the average variance extracted should be more than 50 and 0.5, and value of composite reliability should be more than 0.7. So are you with me till this point of time? Am I making myself clear? Or am I making any sense to you people regarding the convergent validity, these two measure of convergent validity? Okay. So then we'll go ahead with the third measure of convergent validity, which is so this is just the previous continuity of the previous measure, that here you can see the item collectively, they have a reliability of 0.49, which is much below than the 0.70. That suggests that there is a convergent validity is not met. And third approach is the measurement of factor loading. So what you can see in factor loading, that if the factor loading is typically less than 0.5, then you will say that it is not met. If it is more than 0.5, then you can say that it has got a good convergent validity. But generally, this is for those situations where you don't get output in the form of average variance extracted and composite reliability. Those are more objective way that you can see, so that you can decide upon those two measure. Coming to the divergent validity. What is a divergent validity? It is also known as the discriminant validity. Both divergent validity and discriminant validity is same. So what does this mean? That means you have seen in the factor structure of empathy scale that you got 3-factor structure. So convergent validity means like in one factor, all the items, they are highly correlated and they are measuring the first factor, empathy. Empathy means, let's say it is the emotional empathy, the first factor. I have just given a name. What is discriminant or divergent? Since there are 3 factors, so factor 1 and factor 2, they are a little different. So we cannot say that they are entirely different. Why? Because if they are quite different, they cannot measure the one underlying construct of empathy. Remember, we talked yesterday about a generalized construct, hierarchical concept of construct. Can you recall that? So we discussed that empathy is there as a primary construct and then it is a part of a secondary construct and so on. So if you think theoretically that empathy is now broken down into 3 constructs, then the 3 construct would be like social empathy, the emotional empathy, and cognitive empathy. So divergent or discriminant validity means that the factor 1 or the emotional empathy will be slightly different from the social empathy. Similarly, the social empathy and emotional empathy will be different from the cognitive empathy. So they are somewhat different. They are not exactly the same. That's why they are broken down into the 3 factors. So I think similar example, imagine you have different ideas or concepts that you want to measure emotional empathy and cognitive empathy. So divergent validity, make sure that these two don't overlap much, means they should exist as a separate entity. And they should not be very closely related, because if they are closely related, then let's club everything and make one factor to have a 3-factor solution or a 3-factor structure. So if it is a 3-factor, they should not overlap and they should not be closely related with each other. So little overlap is okay. Otherwise, that's why we said that overlap is okay, because then only we can say that it is measuring the same underlying construct, because it is the 3-factor of the same construct, which is the empathy. But this distant relation, that we call it as a discriminant validity. So coming to how to measure the divergent validity. So if you see in the Amos and many of the articles, they have shown the ways of Pearson's correlation, that R and R square measure and average variance extracted. They make a table sort of thing and then they compare to see whether that works or not. But in JASP, this method to measure divergent validity, the most common one is most commonly, like, it's the recent one, and it is easy to done, because that you have to enter and do it manually little bit. But in this case, you get this measure, and this is known as the hetero-trait mono-trait ratio. Now there are 2 terms here, hetero-trait and mono-trait. So hetero-trait is for the 2 different factors, and mono-trait means for the all items in one factor. So what is this? So basically this HTMT is a ratio of, in the numerator, it is the average correlation between, remember this term, average correlation between items of factor 1 and 2. I'm only doing this for factor 1 and 2. Let's say there are 2 factors. So average correlation between items of factor 1 and 2. And in denominator, you take under root of average correlation within factor 1. So here in the denominator, you take average correlation within factor 1 and average correlation within factor 2. Again, we are showing what calculation generally is happening in the background. You get these measure as a part of output in JASP. So you don't need to calculate this. So don't worry. But you should know by definition what is this HTMT, or hetero-trait mono-trait ratio. So we have just shown it with one example. So suppose we have got 2-factor solution of this empathy construct in EFA, emotional empathy and the cognitive empathy. So if you take the items of emotional empathy, so EE1 represents item 1, EE2 represents item 2, and EE3 represents item 3. Similarly, for factor 2, which is the cognitive empathy, CE1 is for item number 1, CE2 for the item number 2, and CE3 for the item number 3. So this is the correlation matrix between the items. So if you see between the same item, if you can see this, and this diagonal represents the one line. So this is the diagonal having one correlation. And then you can see this EE2 and EE2, it will be 6, E1 and E2. Or similarly, this is 0.65. And between C and E also there is a correlation. So heterotrait means you will take correlation between the E and C, means between the items of two different factors. So this EE1 and CE1, you take correlation of this, EE2 and CE2, EE3 and CE3, and so on. And you take average of all these correlation. So you add all this and divide it by 9, because there are 9 correlation, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it gives you the average of correlation, 2.75 divided by 1, divided by 9. And then you calculate within factor 1 and factor 2. So this you calculate. If you see this, here you can see this is a within thing. So within factor 1. So if you see the correlation between EE1 and EE2. So this is EE1 and this is EE2. It is 0.6. If you see the correlation between EE1 and EE3. So EE1 and EE3, it is 0.65, because you have to see the correlation between the same, and then it is 0.70. So this is between the correlation amongst the item. So the average is 0.65. Similarly, you have calculated it for the CE1. So in between the C, you have to take this one. So 0.5 between CE1 and CE2, 0.60 between CE1 and CE3, and 0.62 between CE2 and CE3. And you take an average of this, which is 0.59. So are you getting what we are talking? Please say yes or no. Have you understood up till this point? Saurabh is writing yes, Priyanka is writing yes. Okay. Samina is also writing yes. Okay. Thank you. So you can see that here what we are doing. Let me raise this. So in the previous one, what we did? We took out the average between the factor 1 and factor 2. So we took out all the correlation between these two factors. And next, within factor. So the formula is, if in between two factor, if you want to calculate the divergent or discriminant validity, so it will be 0.305 divided by average correlation between within factor 1 into average correlation within factor 2. So value comes 0.49. If you see this, value of HTMT is 0.49. And what should be the value of HTMT? If you see, a common threshold, it should be less than 0.85. So if it is less than 0.85, that means, so you can say that the divergent validity is met. Now coming to the concurrent validity. So till now we have done, Dr. Om Prakash is asking correlation average within and between. Yes, right. So, so have you understood? So we have talked about the content validity. We have talked about the construct validity. Construct validity is of two types: convergent validity and discriminant validity. Convergent validity is measured by 3 ways. First is the average variance extracted, where you take the average variance of all the items which is getting loaded on one factor. The second one was the composite reliability. It is different from the Cronbach alpha reliability, unidimensional reliability, because it takes the error variances also into account. And you have seen the formula also, that error variance formula was there. So composite reliability, the value of average variance extracted should be more than 0.5. That means more than 50%. The value of composite reliability should be more than 0.8, like we say for the Cronbach alpha. And the value of this hetero trait, mono trait, its value should be within 0.8. It should be less than 0.85. If it is less than 0.85, that means the discriminant validity is met. Now coming to the third type of validity, which is also known as the concurrent validity. Actually, it is a part of validity which is known as the criterion validity. So criterion validity is of two types, predictive validity and concurrent. But predictive is like, it's a follow-up study. You are making predictions, a model based on some follow-up study, then that can be done. So that is not very commonly done validity in case of a scale, because study design is very different for that type of validity. So what is concurrent validity basically? So it is like you check this scale with some other scale also, which is a standardized scale. So it checks that the new scale, let's see this, you have designed a new scale. So generally concurrent validity is done if you have designed a new scale or if you have modified the existing scale. So you compare it with some other gold standard or other established scale, and you give both these scales to the same person and get the score. So for example, if you have to compare this concurrent reliability of TQ, which is the Toronto Empathy Questionnaire, then you can do it with, there's another scale to measure empathy, which is the interpersonal reactivity index. So you get the score, how you will do? So you will choose established scale, which is also you can say that equally good, or maybe if it is a gold standard, then this is very good. And then you administer both these scales simultaneously to the same individual, and then you calculate the correlation coefficient, R. And then you interpret, if the value of R is good, you say that concurrent validity is good. If the value of R is poor, you can say it has got a poor validity. So you can see that we took few snips, like there are 10. If you see, there are 10 individual here. And in this case also, you can see the TQ score is like 45, 38, and the IR score is all, this I score is also very much near to that. If it is 38, it is 36. If it is 50, it is 49. If it is 48, it is 47. So very high score. So this is example of a high Pearson correlation. If you see this, if person is scoring TQ 45, then on IRI it is 30. On TQ 38, then IRI it is 45. So the correlation coefficient is 0.1, which is a very poor correlation. Where if you see here, the correlation coefficient is 0.95, which is very good. So anything better than 0.7, you can consider that as a good correlation. And then you can say that the concurrent validity of your scale with other standard scale is good. And if the correlation is good, then you can calculate the sensitivity, specificity, and ROC analysis also with that particular scale. You can decide what is the cutoff point and all. So this was regarding the validity and the confirmatory factor analysis. I will demonstrate how to do this. But before that, there are a few model fit measures. But I'm not telling you the statistical thing behind these model fit measure, because that is not required for you people, for all of us, for us also. So you should just see the reference, means whenever such value comes, just see the value and decide, because it's a too many indices are there. So you have to see the range or the value. So the first is your chi-square value, ratio of the chi-square and degree of freedom. So generally, if you say chi-square test, it should be more than 0.05, the p-value in this case, because the null hypothesis says that the model, it is a good fit. So if you if you accept null hypothesis, it is good for you. But generally, since sample size is always large in this case, so you will see that this is never fit. Like you will always get a value of chi-square less than 0.001. So you cannot say that the model is not fit. So generally, that's why there was invent of these comparative fit index, because the chi-square value, it will always get failed. So that's why you just report it, but you comment on the other fit measure, which is the comparative fit measure. So what are the value of, these are the names of these comparative. You call it as a CFI, which is the comparative fit index. More than you just remember the acceptable. More than 0.90 is acceptable. There's another indices, which is the Tucker-Lewis index. That is again more than 0.90 is acceptable. There's another measure which is known as the root mean square error of approximation. Lower value is desirable in this case. So less than 0.08 is acceptable. If value is less than 0.06, it is excellent. Similarly, in case of this SRMR, standardized root mean square residual, the value should be less than 0.08. Coming to, there's another like goodness of fit index, which is more than 0.90. And there's a Kaiki information criteria and Bayesian information criteria, which we call it as AIC and BIC. But again, this needs to be compared with the previous model. So generally, what we recommend, you comment on the comparative fit, the Tucker-Lewis, root mean square error of approximation, and standardized SRMR. And if you see the output of JASP, there are 10-15 model fit indicators, but don't need to report and see everything. For us, these 4 are more than sufficient. So let's see this in the data set. I think I will go. So now you have to do this CFA on the other set of the data. And this is the 160 data. So you open this, I think we have shared the data set with you, the prior one. So there is some issue with that data. Okay. But updated taken. So you can see that we have shared the updated also. There was some issue of the commands of that data particularly. So I was trying in that data and these values were not coming. So we did some, we did not do any modification, but there was some issue with our computers. So we have shared the another file with you people, and it is requested from all the mentors that it might be that if you import that data, if you see that edit data, then you can find that these variables, if it is in ordinal scale, change that variable. So we have changed, like you can see here, we have changed all the variable to scale. But if you import the CSV, you might find that this is in the ordinal thing. So if you click here and if you click like this, you can change it to scale. Since I have changed it to scale, so that's why it is already appearing here. So do this before you start, otherwise it will not take. So now coming to the confirmatory factor analysis of this data set. Already it was there, okay. So now you can see that there are variables here. And this is factor. So now you have to enter these variables into respective factors. So we proposed a 3-factor structure. So you note down, all of you, the result of oblimin. because oblimin in the exploratory factor analysis. So I have noted down for myself, and in factor 1, there were 6 items. Item 4, 7, 10, 11, 12, and 14. So I will enter these items. So item number 4, and press Control. 4 on your computer. 4, 7, 10. Then 11, 12, and 11, 12, and 14. You can enter this in factor 1. Now, can you see a plus sign here? So add this plus sign here. In under factor 2, there were 4 items, 3, 5, 6, and 13. So I will enter 3, 5, 6, and 13 in factor 2. And then factor 8 and 9 in factor, item 8 and 9 in factor 3. So 8 and 9 in factor 3. And I will not enter these factors, factor 1, 2, 15, and 16, because these factors, they did not get loaded on any of these items did not get loaded on any of the factor. So I have left these 4 items, and I will propose my model only with these. Out of 16, I have kept only 12 items, and I have not entered the 4 items. And then I will see what are the values of my model fit indices, and what is the value of standardized coefficient, and what about the concurrent value, what about the convergent validity, and what about the discriminant validity. So it takes some time. You can see it is like it takes some time. You can wait, and then again it will appear. Okay. So we'll start one by one. So if you see this, you don't have to do anything in this second order factor. You don't have to do anything in this right now in the model option. You don't do anything. You only go to this additional output. It will be like this. Go to additional output and click this additional fit measure, KMO test, Bartlett's test of sphericity, because that is also you have to test that. Then again, these are the these are the 3 which we talked. Average variance extracted, hetero-trait, mono-trait ratio, and reliability. Have you seen that? We have discussed these 3 measures of convergent validity and discriminant validity. And there is something known as the modification indices. You also click that. By default, it is 3.84. But these modification indices, if you see, and if you take modification indices which are more than 10, and if you do some changes in the model, your model fit indices might improve. That we will see if it is already coming bad. And then if you go down in the plots, you click this model plot and click this show parameter estimate under the standardize this thing and show variances. So these many options you have to click. Now one by one, once we will see the output. So if you see the chi-square, the value, what we did, ratio of chi-square and degree of freedom, it should be less than 3. If you see this was the ratio of chi-square and degree of freedom should be less than 3. What is the ratio here? The chi-square is 345 baseline, and this is 66. If you even see the factor model, it is 97 divided by 51. So that is okay. So it is less than Yes, yes. So it is good fit, na? Less than 2 is a good fit. If you see the ratio, less than 2 is excellent. So it is saying that your model is excellent if you see the ratio. But the other, we'll see the other fit measure also. But if you see the factor model, we have said that this factor model, this is significant. So this value will always come significant because the sample size is large. Now coming to the other fit indices. So I asked you to see only 4 fit indices, which is the comparative fit index. The value should be more than 0.9, but it is 0.83. A little compromised one. I'll write with this. So if you see, it is 0.83. So it is compromised a little. For Tucker-Lewis is also, it should be more than 0.8, it is 0.7. Again, you can see a lot of other model fit indices, but you don't have to report these. Now I'll come down and you can see the other fit measures. So other fit, we remember we talked about the root mean square error of approximation. These two. So value should be less than 0.08. So yes, its absolute value is less than 0.08, but if you see the upper bound, it is more than 0.08, this 0.98. So we are still, you have to report this. And then if you see the SRMR, its value should be again less than, if you see the value of SRMR, its value is 0.07. If you see this reference, so SRMR less than 0.08 is acceptable. So you can say that it is since 0.07, so it is acceptable. So you are getting a mixed sort of model fit. You can say that your model is seeing the ratio of chi-square and degree of freedom, and the RMSEA, the upper bound is definitely crossing, but at least it is within, you can say that the absolute value is less than 0.08. The SRMR is also less than 0.08. And you can see the Tucker-Lewis and this thing nearly this thing, because it should be more than 0.9, but it should be more than 0.9, but it is 0.83. So very near to that, you can see. And then you can see the KMO. If you see the overall KMO, yes, it is not that good. It is 0.69, but it is at least acceptable. You cannot say that you cannot do a CFA. So it is acceptable. Bartlett's test of sphericity, you can see it is significant. Coming to the parameter estimate. So this is like this table. If you see this table is like a regression table where these are the factor, these are the indicator, these are the loadings, standardized loading. This is the standard error, Z value, P value, and the 95% confidence interval. So since all these factors are getting loaded, so that's why you will see that all these loading is significant. If you see the P value of these standardized loading, these all are significant. So you have to report this table, this one. This all is significant since we have taken only significant factor item into that particular factor. Now coming to factor variances, this table you can see, and you can see that all factor, it is estimate is set to 1. So why it is done? Because it is a customary that you set the variances of all these factor set to 1. And then what other measure do you see that is in proportion or relative to that? So no need to worry and don't need to report. This is the way CFA is done, that all the factor, the variances are set to 1. So just remember this, that for comparison, all the factor variances, they are set to 1. So don't need to report this table. This is understood and implied. Now coming to factor covariances. If you see the factor covariances between factor 1 and 2, this we will use. We will see the estimate. The value of this factor covariances, it should not be more, here if you see, so it is generally more than 0.2, 0.3, 0.3 and 0.5. Value should be between, you can see that it has got a good covariances, all the factor 1 and 2. Now coming to, we will not see these residual variances now. Coming to the average variance extracted. This is the average variance extracted between factor 1 and 2 and 2 and 3. So you can see the value of, what was the value of average variance extracted, what we did. So for factor 1, it is only 0.21. What should be the value of average variance extracted? Yes? All of you, please guide me.
More than 0.5.
0.5. More than
Yes.
0.5.
Yes. So none of, even you can see that only in factor 3, it is little bit near 2.5, which is item 8 and 9. Here you can see 0.46. Otherwise, in other case, you can see that convergent validity. The two types of construct validity, convergent and discriminant. So convergent validity, that is not met. And if you see the before heterotrait monotrait, we will comment on this. So if you see the coefficient gamma or alpha, Cronbach, or no, don't call it Cronbach, we call it coefficient. So none of the value is above 0.7. It is near 0.6. So again, you can say that convergent validity is not met. Again, coming to heterotrait monotrait. If you see this, what was the cutoff of heterotrait monotrait? It should be less than 0.85. So yes, whether that divergent validity is met or not, seeing the heterotrait monotrait is between two factors. Remember how we have calculated it? So this is the HTMT of factor 1 and factor 2. This is the HTMT of factor 1 and factor 3. Here you can imagine that something is written. Like I can tell that you think that here it is factor 1. I1. This is I2. And this is I3. So this is between I1 and I3. This is between I2 and I1. And this 0.56, it is between the. So all the values less than 0.85. Yes. So divergent validity is met, but convergent validity is not met because you can see the value of average variance explained. It is less than 0.5. And this is also less than 0.7. So till now, have you understood this? You have to report all these things in your write-up. Have you understood up till this point? Then I will go for explaining the path diagram and how to modify your existing model a little bit.
Madam, HMR, I cannot get it. Means I1, between I1 and I3, it is,
This is I1.
yes.
So for I3, I1 is this. This is I1 actually.
Right.
Means I have written, by mistake, I have written I1, but it is F1. Why? Because you do it with, by mistake, I have written, consider this as F. Sorry.
Understood, ma'am. Yes,
I'm sorry.
So F1 and F2, it is
Yeah.
0.57.
Between 2 and between 3.
Okay.
This is factor 2, and here you imagine, let me erase it.
Right, 0.56, 0.57, okay.
Yes,
So,
it is, I'm not writing factor as I'm very slow with this pen. So just think this is factor 1, 2, and 3 here also.
Yes.
So this is between 2 and 3, 0.57. This 0.3 is between 1 and 2. And this is between 1 and 3, 0.25, 245. Okay, Dr. Nitin is asking to explain model fit. Okay, I'm explaining. So I'll erase this. You can, wait, I don't want to draw. Yes. So these are the model fit indices. There are three types of model fit indices. First is your absolute model fit, which is the chi-square test. And generally, we take the ratio of this chi-square and degree of freedom. So if the ratio of the chi-square and degree of freedom is less than 3, if you see this, you always refer this table, because it may be possible that you will not remember all these values. So I've said that ratio of chi-square and degree of freedom, if it is less than 3, it is acceptable. If it is less than 2, it is excellent. So if you see this, if you take out the factor model, the chi-square and this thing, if you take it as 100 and you take it as 50, so generally it will be 2. Or Dr. Shamshad has calculated it, it is 1.9. So if it is 1.9, you can say that it is an acceptable model. So first conclusion you will write on the basis of chi-square test, that it is a good fit, very good fit. Coming to the additional, if you see, these are the additional fit measures. So additional fit measure, there are like so many here, but it's good that you only comment on 2, which is the most common one, which is the comparative fit index and the Tucker-Lewis index. So if you see the value of comparative fit, in both the cases, it is more than 0.9. If I go here, you see the comparative fit index and TLI. Both these CFI and TLI, the value should be more than 0.9 is acceptable. Can you see this? So for first one, the ratio should be less than 3, or if it is less than 2, it is good, very good. For comparative fit index and Tucker-Lewis index, this should be at least more than 0.9. Coming to, again, other indices, like these you don't have to see, information criteria, because this Akaike information criteria and Bayesian information criteria, this is just to, even the log likelihood, you see the reduction of log likelihood. So if you want to compare two models, suppose there in the exploratory factor analysis, you use both type of rotation. You use one time Promax and the other time Oblimin. So you will have two model, and you also test the orthogonal, and maybe 1-2 type of orthogonal rotation. So you will have 4 models. Then you keep on entering the items taking according to those factors which they have suggested. So it depends on you. It is a very, I should not say Herculean task, but if you want to test everything, then you can do. That is a learning exercise. Okay. But generally, if you want to keep things simple, then you can only take the Oblimin, one rotation, note down the items in that particular factor and test it the way we are doing. So in CFA, no, we don't apply rotation. Do you have any? Rotation to already you have seen in EFA. You don't have any other option also. Rotation is only there to see the factor structure, underlying factor structure. So when the idea is to get the confirmation of already extracted factors, then you don't do. Yes, in EFA, you might have 2 to 3 different types of model. Model, what I means the different items getting loaded on different factor, and maybe the factor structure, 4 factor, 5 factor, or 1 factor or 2 factor. You can keep if you keep the factor loading up till 0.4, up till 0.5, you may get only 2 factor structure. So it is up to you. You can propose 2-3 different types, and you can see the model fit. If in 2 factor structure, if your model fit measure is good, then you can decide for 2 factor structure. Are you getting my point? So in CFA, the structure is already fixed. you don't have the freedom of exploring factor structure here. You have already done that in EFA, and you will make a note of all those models. If you want to try different models, you can have a note of like model 1, 2, 3, 4. You can have a write-up, and then you can try all models here, and then you can show the comparative fit indices. That if a particular model, if your comparative fit indices are improving as compared to this oblimin, then you can propose that that model is better. Have you understood up till this point? Okay, so I did not explain that RMSE. So this information criteria you use only when you compare it with other models. Otherwise, if you see this, so you basically report this root mean square error of approximation and SRMR. Okay, and if you see the value here, the value of, in both the case, it should be less than 0.08. This one. Okay. So if you see the value, both are giving a good value. It is 0.07. But if you see the upper boundary, because we see that the upper bound of RMSE should also be less than 0.08, but it is 0.09, but still it is okay. So you can say that it is not, the model fit measures are good rather, except for this CLI, which is less than 0.9. All there are 3-4 measures which are showing a good model fit. But again, you can improve these also a little bit. And that's what I want to. So have you understood, Dr. Nitin?
Yes, ma'am, understood.
Okay, thank you. Then I'll go to these modification indices. So you can see the modification indices of these factors. And modification index of, if it is more than 10, then you can try doing the covariances, but none of the modification index is more than 10. So I'm not improving. Like in this case, if one modification index in this case, if it was more than 10, then I could have entered those modification index in the, here in the model option. You can see there is a residual. Okay, there's, oh, this one, sorry, residual covariances, this one. Yeah. See this. So in this case, the modification index, because I have to see the modification index of the covariances. This is for the covariances. And yeah, here I will enter these and I will see how the model is performing. So what are the two items which are having a modification index of more than 10? Because we have to look for the higher values. And generally we keep the value more than 10. So these are the two items. Item 14 and item 11. And again, there is one more criteria that these items should be of the same factor. If the modification indices are of some different items of the two factor, then you cannot show that. Yeah.
Hello.
Pardon? Yeah.
Hello.
Yes, yes.
Hello.
Yeah, I'm listening to you, Dr. Tapubrata. Yes, yes. Do you want to say something? Okay. So you can see that this arrow you can see. This is between the item 14 and item 6. But these modification indices should be of the same factor. So if you see the 14 is in one factor and 6 is in the other factor. Similarly, 11 and 13. 11 is in one factor and 13 in some other. So if you see this, all these are in some other factor. So that's why we will not enter this in residual covariances. If you see this 7, 12. So 7 is in factor 1 and 12 is in factor 1. Yes, you can take this. Just for demonstration, I am showing 7. Let me take out this. So this 7 and 12. This one. and 7 and 11 also. This one. Any other? 4, 5. No. 4 is in one and 5 is in other. 11, 14. Yes, 11, 14 can be done. Are you understanding what I am doing? Are you getting what I am doing?
So in the same factor, if the items are in the same factor, you are applying the covariance only if it is more than 10.
Okay. Yeah, so I have understood. So there are many no's. Yes. So why there are no's? You see the residual covariances. Covariances means these two items are strongly moving together as compared to other. So if you put these items in this covariance matrix here, if I shift these items here together, I'll show you, then your model fit indices will increase. So these are to modify your models. And that's why this is a modification index, means your model will improve if you enter these together in the residual covariance matrix. We try, but the point is that they should be in the same factor. So we can reduce the error by adding these covariances. If you increase, if you put this, like these are the 8.4, if you see this 8.4, so we can reduce this error by 8.4 if we have these in the model. So I will just show you. Let me erase this. I will show first you the path diagram. But for path diagram again I need this. So can you see this path diagram? Can I enlarge this? Okay. Is it visible? You can see this is factor 1. This is factor 2. This is factor 3. Factor 8 and factor 9. Item 8 and 9. It's getting loaded. So you can see factor 14, 17, 10, 11, 12. Sorry, for factor, I got mistaken. Item 4, item 7, 10, 11, 12 and 14. These all are together into the factor 1. And this you can see, this is the factor covariance. So it has set to 1. Remember, there was a table where I said that all the factor variances will be set to 1. So this is all set to 1. And then this item 8 and 9 on factor 3. And these are all the items of factor 2. And these values which you can see 0.9, 0.87, these are the error variances. And this is the respective loading of the factors. If you see the value 0.32, 0.53. So if you see, no, it doesn't. It comes. It takes some time. So 0.32. If you see this standardized loading of item. So that was a factor 4, 3, 4. So these are the values. I think there is some less value as there in the table. So these are the loading of these items into this factor. And these are the covariances. 0.4 between factor 1 and 2. And this is between factor 2 and 3. And then if I put these two, like what I remember, factor 7 and factor 11. So factor 7 and 12, what I do, factor 7 and factor 12. In that residual covariance, if I shift that, you will see that it takes some time. And there will be appearance of covariance arrow here. So in a path, this is known as the path diagram. In a path diagram, the factor is expressed as a circle and all the items are expressed as a square. And then this is the direction of arrow which we have seen in the reflective scale. this in between factor, it is the factor covariances. This dashed line is for the factor variances. And these are the error. So it is buffering, you can see. No time लगता है इसमें. So can you see now there is a line appearing in between factor 7 and factor 12. Can you see this line? Is it visible to everyone? Now, if I have attached these two, my model fit measure will improve little bit, not too much because the modification index was less. Here it was only, and that has disappeared from here because I have entered these two here. So if you see, initially it was 0.83. The model fit, which was the comparative fit index, if I go up, so it is now 0.86. Can you see it is it is 0.86. Remember, this is 0.86. And RMSE, if you see this, it has also come little like 0.06 or 0.07. So I will put these covariances also, then we'll see. Remember, it was 0.86. So the next was between the factor, no, this is there, 11, 14, 16, no, 11, 13, no, 4 and 5, again no, 3 and 6. Yes, 3 and 6 in the factor 2. So 3 and 6 I can move. So 3. Okay, it has gone here, no? It was 7 and I'll do 7 and what was that? 7 and 12, no? So 7 was here. Okay, so I have to select it. So 3 and 5. 3 and 5.
3 and 6.
No, 3 and 6 will be different, no? 3 and 5 we have, 3 and 6 we have, both are there. So 3. 3 and 6. 3 and 6. That I move together. And then see the other residual covariances. It is taking some time. But you see these residual covariances, when you put this into the table, that means the error will go down by that particular value. And there will be a slight increase in the fit indices. But generally it is suggested you should choose more than 10. But you don't show too many covariances. It is said that just don't keep on putting these just to improve the model fit measure. Wait, I'm waiting. Now it has stabilized, if you see. So it is 0.88 now. So from 0.83, it has come to 0.88. So if you take only up till 1 decimal, that though it was there initially 0.83 after that, so it is nearly 0.9. So by these little modification, you can improve your model fit indices. Okay. Here also, if you see the upper bound of RMSCA, it has gone down to 0.08 from 0.09. Okay. So have you understood up till this point? And then you can that's what I'm saying. You can see there are 2 residual covariances which got attached, 3 with 6 and this 7 with 12. And if you copy this, you can copy this or you can save it as an image. And you can save it and then you can use. Okay, this is in the form of a graphics. So you can just show in the confirmatory, this is the path diagram and you can report the other measures the way and you can write it in the write-up. Okay. So do you want any steps to be repeated? Otherwise, we'll go to the breakout room. Anything do you want me to repeat? Okay, if not,
ma'am, I don't understand. Don't understand how we selected 3 and 6. On which basis?
okay. So you have to see this output. Residual covariances. This is the table of residual covariances. So it has shown you the covariance. Can you see this sign? This sign is of covariances. So these are the items which are co-varying, like item 11 and 15, 10 and 8, 4 and 5, 11 and 13, 14 and 16. We have
Yes.
moved these 2 items here because it was initially here only in this table. So, but we will move only those items here which are belonging to one factor, single factor.
Okay.
Like if I move, yes, I will show them. This one, can you see this? That's why you have to keep a note of, since I have written it on the piece of paper. So you can see, you can only make covariances among items of factor 1 or factor 2 or factor 3. So that's why I have selected only those items which were belonging to one factor. So that's why I have
Okay.
selected these 2 because they were belonging to the same factor. 7 and 12, 3 and 6.
6.
Then again, you can, although you can see 14 and 16. Sorry, 14 and 6. It has got 14, very highest modification index. But I will not move these 2 in this box. Why? Because they belong to, one item belong to factor 2 and the other item belong to factor 1.
Okay. Thank you, ma'am. Thank you.
Anybody else? Yes, covariance should be in a single factor, true. Anything else? Anyone? Okay, then Dr. Akash, can you please